Okay, and welcome back to System Software. Today we are on the last part of our tools intro, where we're kind of giving you a crash course on the command line, version control, build automation. You'll use all of these tools throughout the semester for all your programming exercises and your projects. Today we're going to go over build automation. But before I do, let's go over homework 3. So did anybody have questions about this homework or issues with homework 3? Yeah.
What's the second part of the question actually asking?
Yeah, that's a good question. Several people asked me, like, I said, okay, so you can see I sort of made a silent edit here.
I meant the second part of the first question.
Oh, the second part of the first question. Oh, sorry, okay. What happens if I already push my repo to grade server, then I create a repo from scratch? How do I get my repo if I already deleted my, it should be my local repo, not my local repo. Let me fix that. So with the change to my, does that make any more sense, or is it still just as confusing?
I think it's connected to the first part of the question, or is it a second question in itself?
It's connected to the first part of the question. So this answer is like sort of deeply in the version control exercise. Well, I'll just go over these. I'll just go over these questions. So let's just start with number 1. So what happens if I already pushed my repo to grading server and then I create a new repo from scratch and try to push it? What's going to happen? It's even more, it's kind of like it will be something effectively a merge conflict. So what's going to happen is you're going to have on the grading repo, there's already a repo created, and it may have a commit in it, and then you create a fresh repo and you try to push the changes to it. Well, Git is going to be like, well, you're trying to push a completely different history. It'd be like telling your bank, hey, I didn't have a new transaction. I just want to change the entire transaction history. Can you let me do that? The bank's going to say no, right? So it's supposed to be an append-only log of transactions. So and this is really meant to avoid a common problem that I saw where people would not quite get the concept of the remote repo yet, and they would think, oh, I made a mistake. Let me just delete the directory on Eustace and then recreate everything from scratch. But if you've already synchronized your repository, you've already pushed that commit history to our grading repo, then you can't just rewrite history. Then you'd be able to cheat very easily, right? As well, you could just change the history to make it look like you never made a mistake. So once you push and once you synchronize between these two repositories, you're only affecting your local repo when you're deleting your directory. So there's even it's in here. So this wasn't due yet, so I didn't expect you necessarily to go over all this, but. So here in the directions, when you make the folder, you create the local Git repository. This is a fresh Git repository. And then you add, commit, and then push. Once you add the remote repo and then push. Once you do this push, your log of changes is now synchronized to the grading repo. So if you delete your local repo, you have not actually deleted the remote repo. It's kind of like you uploaded files to some social media site and then you delete them on your phone. Yeah, they're still out there on the social media site, right? So it's same concept here, client-server concept here. And there's even an error here where it says, should be here. Okay, so this error, and so, I'm not expecting you to memorize this entire set of errors, but when you go through this exercise, if you see one of the, it'll list out all the possible, most of the errors that I know of that can happen. It'll say rejected. It'll say I rejected the push. The grading server, the grading Git repo will say failed to push some refs, that's just pointers to commits. They're rejected because it contains work you don't have locally, et cetera, et cetera, et cetera. So this is the message you see when you try to just blow away the commit history on the server. You could probably imagine why this is a good idea to protect against, because you don't want some newbie colleague to just accidentally overwrite your entire source code repository and all the history. And so what do we need to do if we encounter this? How can we resolve this? And if you haven't read this yet, I don't expect you to know, but so what can we do if we want to be able to push again? Yeah.
You have to do the git clone thing?
Yeah, exactly. So this repository exists already on the server. So instead of trying to push over it, first copy that to your local machine by using pull or clone to clone the whole repository, and then start doing your changes. So remember, it's okay if you made a mistake in your code and you push that to the grading server. You don't have to delete your whole repo because remember, just like a bank transaction, you can zero out the bank account by just subtracting stuff. So if you made a mistake in your code, you don't have to start from scratch. You can just make changes to fix it. And you can always just delete all the files, and commit that, and push that as a change. But that's not the same thing as deleting the entire history of changes. You see what I'm saying? So it's telling the bank, hey, I now have $1,000 versus adding $1,000 to your bank account. See what I'm saying? So instead of removing all the debits that you had from your bank account, you add more money, and now you have the balance you want. So if you wanted a zero balance, you don't just say, destroy all the transactions, because the bank is going to lose their money. You just push plus whatever amount your negative zero, and then you'll be at a zero bank account. Questions about that? Does that kind of make sense?
Wait, can you push the clone version, the clone repo, or?
Well, all push does is it just updates the. Let me show you this. So I only did this sort of briefly, the distributed part. And this book, if you're interested, more sort of details of this, they actually have really good diagrams to show this. But basically, when you do push, so this is like the grading server. This is your Eustace or your local machine. These versions are commits. And so if I add a new version here, I add a new commit log, remember it's just a diff, then now the server has everything I have except for that one commit. So if you end up deleting this whole repository, you effectively have an empty repo. But all these commits are saved on the server. So when you clone, you're copying these to the local machine. So you don't have to push anything. Once you make a change after you've synchronized that remote repository, then when you say push, all it does is it just pushes the new single commit because it already has all of the other commits. Make sense? So I know I'm sort of making splitting hairs on terminology here, but just to be really clear about it. Push and pull are for just copying new commits, whereas clone is give me the entire set of commits from the beginning of history. So does this answer, the person who actually answered this question, does this answer your question about this second part?
Oh, yeah.
Is that clear? That's clear? Okay. So yeah, that's how you will get your repo back, because nothing's really lost. It's all, once you've pushed, that's all saved in the remote repo. It's basically like a snapshotting backup system, effectively. I'm sort of a manually controlled snapshotting backup system for your file system. Okay, any other questions on one? Oh yeah.
So a little different from the question in the homework. So at least what I do is right now my Git sends it to a GitHub repository. Does Git have to interact with GitHub, or can it interact with completely different repositories, like Fighter repository
Oh, yeah.
and some custom server?
Yeah, absolutely. So GitHub, remember GitHub is really just a Git server. They have some extra facilities, but they're basically a Git server. So they are, in this picture that I removed, they're just one of these computers. So you can think of them as sort of your de facto official version. But yeah, there's no reason that you couldn't also put GitLab here, or have your own server, have Eustace here. And if this is your local copy, you can push all these commits anywhere. It's decentralized. There's no official repo here that is the one repo, at least not according to the Git tool. You have to tell it what are the remote servers. And all of those are they're all equally official in terms of the Git tool. So that's why it's very easy to migrate to another Git server if you want, if you don't like GitHub anymore, or you don't like GitLab, or you want to host your own stuff. It's also easy to collaborate with others. It's easy to fork, because I can just clone someone's repository, make changes, and then push to a different server. And voila, now I have a so-called fork. But the fork is really just the same repo, but I've made commits that I haven't pushed to the one I cloned from. That's all a fork is in this context. But yeah, good question, yeah. So these totally decentralized. GitHub is just a service for hosting Git repositories, but you absolutely can use any other server you want. Yeah.
On the VC exercises,
Yeah.
I was doing it and I was trying to do the feedback. We should be able to get feedback yet, right?
Right, you won't see feedback. Yeah, I saw somebody ask that. So it's not fully automated, and that would be nice. That's sort of my next step, is once you push, there are hooks that you can automatically run stuff once it's pushed, but I have to work with like the IT. I don't control the server, the Git server. I have to work with them. But once our graders grade stuff, yes, that's where the content will go. And I failed to show it last time because I made a mistake. In my script, I wasn't able to access the Git-O-Lite server. I fixed that now. So I can show you now what it looks like. But once we actually grade, that grade will automatically put a report to that feedback, and then you can do git pull and get the stuff. But right now, yes, it'll be empty.
And you should, and to double check, just to make sure we did everything right, we should just check if the repository exists on the server.
Yeah. Just follow along with the those like validation steps, where it says, make sure you have, git log has 2 commits in it. I think it's like, should be in here.
That's the very bottom.
So that's a grading schema, and just, as you go through, just do all the validation. If you do all the validation and it's right, that's basically what our script does. Our script literally just clones it, so you get 3 points for it exists. It looks for a file called readme, and then it runs git log and sees if there's 2 entries. That's all the grading script does. I can show it to you if you want. It's just a pretty simple bash script that literally just clones the repository or updates it if it exists already, checks to see if that directory exists, that is, it worked correctly, checks to see if the README file is there, and you get 0.5 points, and then counts up the number of commits, you get 0.5 points. That's it, and then just adds those up. So that's it. That's all the grading script does. Yeah?
So as long as we follow,
sorry.
like, the steps, like 1 to 8, and all of the validations went through correctly, that's all we have to do? We don't have to submit anything?
No, so once you do push, that is submission. So in this class, instead of using some bespoke submission service or web courses, we just use Git, because Git is by nature synchronizing code. That's what it's for. So by pushing to our server, for this class, the de facto official server is the submission server, Eustace 3. And so as long as your code is there, we can grade it from there. We have access to it. Yeah. You figured it out? Okay. All right. Sorry about that. Okay. So good. Yeah, good questions on version control. So has anyone done the version control exercise yet? I've gone through it. Any issues at all? Well, all good? Okay. So yeah, it took me a couple semesters to get this documented well enough to handle everyone's, all the repeated mistakes that I saw from lots of different people. So hopefully it's clear, and it's really like a paint by numbers. Here's your intro to using Git, and because you're using it on the command line, you don't have the benefit of an IDE to do it for you automatically. But here you actually learn what Git is doing a little bit more behind the scenes. You won't. If you get merge conflicts or you have any issues with your IDE, when you understand what's happening under the hood, it'll be much easier to figure out what's going on. You won't just be beholden to the IDE. Man is not made for the IDE to be a cog in the machine. The IDE is made to help you. So you have to understand your tools in order for them to be effective for you. All right, any other questions on homework? Oh yeah, I didn't finish the homework. Any other questions on VC or homework? All right, so I made a little sort of weaselly edit here. Before I said affected, and then some people had the good point that, if you do git pull, are you affecting both the remote server and the local server? In some sense, yeah, because you're reading from one. So I changed this to be modified. That was sort of what I originally intended. If you put anything else, that's fine. Remember, it's not graded for correctness. So you had the right idea. I was vague in my question, so that fault is on me, not on you guys. But I was intending modified. What gets changed. But I didn't say that. I said affected, which is more vague. But okay, so let's go through this. So I put Emacs. Emacs is not a Git command. What part, so these are your 4 parts. Working directory is your local checked out copy of the code, your local checked out copy of the one version of the code. Staging area is where you collect together changes. Before you commit them, the local repository is the list of commits. That's the diff plus metadata, like who made the commit and the date of the commit. And the remote repository is the same as the local repository, it's just on a different server. So Emacs, what part of the Git repository are changed by? So I heard working directory. Anyone say staging area? No? Okay, good. Working directory. Because Emacs is just editing files, and it's editing files in the checked out version of your repository. I guess technically you could mess with the .git folder, but let's ignore that for now. All right, so git add. What's changed here? Right, so careful with use the word push, because push, it's like overloaded. But yes, the contents of the working directory, or some contents of the working directory, are now reflected in the staging area. Some diffs are being stored in the staging area. So if you had said working directory and staging area, that's totally fine. The working directory isn't being changed by git add, but the staging area is. It has new diffs. All right, what about commit? Which section is being changed by commit? Local repository, yeah. So the remote repository is not changed by this. The working directory is not changed by this. It's taking changes from the staging area and recording them in the local repository, along with metadata. Your commit log, date, who's committed it. All right, what about pull? Good, local repository. So there's pulling changes from the remote repository, but those aren't being changed. The local repository is being changed. And then what about push? Yeah, it's the opposite. So git push will take commits from the local repository and copy them to the remote repository, changing the remote repository. Questions on that? So if you understand these 4 areas and you understand these 4 commands, you have like, I don't know, 80% of what, well, maybe not 80%, but 80% of what you're going to do most of the time with Git. Adding, committing, pushing, and pulling. Yeah?
2 questions.
Yeah.
One, so when you commit, does it keep everything in the staging area, or does it actually remove it from the staging area?
I think it removes them. I think it removes them. So that's a good point. So in that sense, it is changing the staging area. That's a good point, yeah.
With
Yeah.
pull, wouldn't that also affect the working directory, because if you have the file open and you...
Yeah, you're right. It does. It does. It does. You're right. Actually, in my answer key. Okay, yeah. So my answer key is more accurate than, so I hate to show my answers, but you're right. So my answer key, I had actually, apparently, so I'm an idiot. So I had forgotten that, yes, local repository or git commit working directory is also changed by git pull, because git pull will check out that latest copy. I didn't put git checkout on this one. And but I didn't think of the staging area as commit. Staging area being changed by git commit, so I'll add that one. So you can see, I didn't have like a real, rigorous specification of what this means. I just wanted to make sure that everyone is kind of clear on what these pieces do and what these sections of the Git are and how these affect them. All right. Well, anyway, there's the answer key. All right. Any other questions on? So yeah, good point. Any other questions on the homework? So do the VC exercise. It's should be pretty straightforward. I think I've gotten it to where it's like very much paint by numbers. You just cut and paste, or I would actually hand type them for now, so you can using tab completion. And go through all the validation, so you can make sure you actually got things right, and you also get more experience using git status, git log, git show, which is how you're going to keep track of the state of your Git repo. All right, any other questions before we move on to build automation? No questions you have? Version control? Okay, so let's move on to our next tooling that we're going to look at, and it's build automation. Okay, so quick quiz. How do you build a C program? What do you do to build a C program? GCC? Yeah, you say gcc-o hello.c. Any questions about this one? Anyone use .-o before? Anyone not use it? -o, you just specify the output file, so it's not a.out every time, that default name. But that's how you compile it, right? You probably learned if you took an intro to C, you probably either used an IDE or you did GCC, right? All right, what if I have 2 C files? You can break your code up into 2 C files, right? You don't have to just compile one at a time. What do I do if I have 2 C files I want to compile? Yeah.
So use the same command, just add a second file.
Yeah, that's it. You just say gcc-o, the name of the binary you want, and then you put all the C files that you want to compile at the same time. Has anyone actually had to do this for class? Or anyone do this before? Okay, not much, right? Mostly we're just doing single C file programs. And that's where there's a big difference between classroom coding and like professional coding. Because what if I have like 30,000 C files? So take a program like the Linux kernel, you've got 20, 30,000 C files that are all being compiled into potentially compiled, not all at the same time, but if we're trying to compile all at the same time, which actually never happens in practice, but if we have 10,000 files that we're going to compile together, this is what we'd have to do, right? We'd have to just make a giant, many hundreds of character, thousands of character command line to actually build them all, right? So why not do this? Or why do this? I mean, is this a good idea? Should we just do it this way? Is this an easier way to do it? Why not do it this way?
It took a long time to compile all the files.
Yeah, it's going to take a long time, right? You have lots of C files. You have to compile them all. But it's our program. Well, we have to compile them all anyway. So you're going to have to compile them all anyway. But most of what professional coders do is maintenance work. You're fixing bugs, you're adding features. Less often are you actually creating projects from scratch, especially not, a 100-line C program. That's less often what you're actually going to be doing in practice. So if we have this, 10,000 C files, and we just make one little change, we make one bug fix in one file, if we just build them all at once, we're going to have to wait potentially hours or tens of minutes each time we want to build. So this is where the technique of separate compilation comes in. Anyone hear about this separate compilation before? Not many people, okay. So if you're doing professional coding or an internship, you probably heard about this. You probably were doing it, maybe not aware of it because the build system is doing it for you. But the idea of separate compilation is we break up the program into separate C files, or separate program files, which is why you might want to have separate programs in the first place. Compile each one individually, and then link them together at the end. So this is an illustration of what this might look like if I've got so let's say I've got a program where I divide up the main method. Let's say I've got a function that'll do squares and a function that'll do exponents. That's just some illustrative example. So the kind of slow way, if I have any changes, is to just pass all of these to GCC and produce my program. With separate compilation, I can actually compile these individually into .o files. So if you've ever seen .o files, when compiling stuff? Nobody? So yeah, if you've compiled code like other people's code, you've probably encountered this before. But .o just means a compiled file. GCC will actually run a bunch of other steps. We'll see this later when we talk about compilers and the back end of language tools. But the real output of just the compilation step is the .o file. It's just C code turned into machine code. And then GCC will also call what's called the linker, which combines compiled machine code into a single program. And so this tool is actually called LD. It's sort of a misnomer for loader, but it's the linker. But GCC will run all these steps for you behind the scenes. It'll run the linker for you. And so now you can see that if I make some change here, I only have to recompile this file, and these two files, these compiled files, can stay the same. So I only have to run the linking step. I only have to combine these object files. I don't have to do these compilation steps. These can stay the same. So that's separate compilation. Questions on that? Sort of makes sense? So if I've got 10,000 C files, then if I only have a change in one C file, I don't need to recompile the whole project. Separate compilation. And how to actually break up your program and depend on other people's libraries. This is more for like a software engineering course, or maybe processes or senior design. But I just want to show you how this is actually implemented, because you'll use this a little bit in class, or you can use it in class, and I'll show you how to actually automate these processes. Okay, so this is what it looks like using command line tools to actually do this separate compilation. So the -C flag is actually the compiler step. So GCC will run all of the steps of the language toolchain, but -C, and you can actually, if you ever sort of forget what these command lines are, you can always go on use this and use man pages. Okay, this is, so it actually says it there, but you can see here, so it says compile or assemble the source files, but do not link. So it's compiling, it doesn't do the linking step, which is actually not part of compilation, strictly speaking. And we'll learn about compilation later in the class. But okay, so here's how you actually compile it. You compile it with -C. It'll produce a .o file. And so in our example, we compile each of these individually, producing .o files. And then we can use GCC to link them together. So it kind of looks like an extra step, but we get this benefit of separate compilation. Yeah.
Do all the files have to be .o files, or can we like mix in .c files?
You can mix in .c files. So GCC it's smart enough to like run the compilation for you. So it does this. So this is an example of a program that actually does look at the extension and use that to tell it whether it's like a C file or an object file or an assembly file, and run the appropriate tool. Okay, so let me show you what this looks like. Oh yeah, sorry, question.
The O flag isn't what actually links it, right?
No, the O flag is just the name of the output file, the executable output file. So it's like an argument to the linker.
Okay, so we don't have to specify that we want to link and it will just know.
No, it will, GCC will infer that's what you want to do from the -O and from the input. Well, that's what GCC by default will run. It'll run all those tools. Running the linker by yourself is a massive pain because there's all sorts of extra library stuff that you have to, and we'll see that, as I said, the second half of the semester we'll actually see the details of that. But no, GCC will by default try to produce an output binary for you.
Okay, and just to clarify, so when you run that command, it goes through the whole suite of GCC tools?
Yeah, when you run GCC by itself, it'll go through the whole suite of language processing tools. Okay, so here's what this actually looks like. Let me save this over here. So here I've got my C files, and the contents really don't matter that much, but I'll just walk through them really quickly anyway. So this is just a program that calls square on the number 3, but square and exponent aren't defined in this program. They're instead defined in other C files. So here I have the square function defined in this C file. It's a separate C file, but it calls the exponent function, and exponent is defined in this C file. So this is what separate compilation allows. It allows effectively libraries, or allows separation of implementation. And you can even, there are other tools for even having code reuse outside of your project. These are libraries. But okay, so those are my 3 C files. And I can individually compile them. So when I run gcc-c, now I've got main.o. I run for main.c, I run gcc-c on square, and now I've got square.o, and so on. So those are my compiled object files. And then finally I can combine all these .o files into a compiled binary to create my executable. Questions on this? Does this sort of make sense? So this is the same thing if you just copied all these into a single C program and compiled it, you get the same program. Yeah. The order of the files effectively doesn't matter. There may be some issues with how errors are reported if you put them in, like if you have the same, duplicate function definitions, but yeah, effectively the order doesn't matter, yeah.
So will this make it easier to edit one thing and then compile, so you don't have to recompile everything?
Yeah.
Is there some way to make, like, the example you gave earlier, 30,000 easier to type all of that out?
Yes, there is. That is actually build automation. That's what I'm leading up to. So there are tools that will allow you to specify this process so you don't have to do this by hand. That is what build automation will do for you. So just to show, to kind of bring this full circle, let me make a change to this program. Let me take the square of 4 instead. And now you can see, do I have to, I just changed main.c. Do I have to change square.c and exponent.c? I shouldn't have to change it, right? And I don't even have to recompile those. I can just recompile main.c using gcc-c. And so now I get an updated version of main.o. So you can see main.o is now 1243, but these are older compilations. And then I can just, so this doesn't wrap, then I can just rerun my linking step. So I haven't edited square.c, I haven't edited exponent.c. So I don't need to recompile those. Those are already compiled. I can just relink with my new version of main. And what should I see when I run this? If you've been following along, square of 4, 16. So it still works, right? I didn't need to recompile the whole program. I just recompiled the one C file that I edited. Questions? Okay. All right, and so I went through this already. So you modified one file and you just recompile that one file. Yeah.
Do you have to do the GCC -C? Do you have to separate that each line for one program, or can you also do multiple of those?
I think you can do multiple of those in one line, and I don't remember. Yeah, it shouldn't link them. Yeah, actually, I'm not sure. Let me see. It may not allow it actually. Yeah, it does allow it, and then it's still separate files. Yeah, so you can do that. But okay, so I'm showing you all this just to illustrate, manually how you do separate compilation. But as you can see, it's very verbose. It's kind of a pain to do this. So in comes build automation. This is what build automation is for: is to take these more sophisticated setups, organizations of your projects, like these build setups. If you have a massive project and you want to do separate compilation, or you want to automatically run the compilation, so you don't have to remember the command to run, import dependencies, import libraries, generate documentation, run tests. This is what build automation is for. It's programming the software operations side. So if you ever heard the term DevOps, you ever heard DevOps before? Oh, not many people heard DevOps. Okay, so this is a huge buzzword in so if you worked in an internship or so DevOps is automating the process of building and testing and running software. So in class, we just learned kind of algorithms and running individual C programs. But in the professional world, programs are millions of lines of code. They have complex dependencies on other libraries. They have documentation that needs to be generated, automated tests that need to run. And build automation is the set of tools and techniques that have built up to help developers do this, help automate the operations of software. All right, so the kind of classic tool for doing this is called a makefile. Who's worked with makefiles before? Okay, not many people. So they go back to 1976. They're very old, but they are in very wide use today still for kind of low-level systems C programs. So I show them because they're kind of I don't know, the alligator of the build automation world. They're kind of dinosaurs that still exist today and that are everywhere. Okay, so this is so a makefile, you can think of makefile as kind of like a program or like a specification of a program. It's like basically a domain-specific program for writing build automation, for doing separate compilation and other things. And this is what the syntax of them look like. This is what the shape of them look like. So you write here on the left the target. That's the thing you want to generate. So that's like main.o is the target. So you tell make, okay, this is my rule for making main.o. Prerequisites, this is the file you need in order to build main.o. So what would go here in prerequisites? So what do you need in order to make main.o? What file do you need? Main.c, yeah. So the rule says, you tell make, here's what I'm going to generate. Here's the files you need to generate it. And then we have a list of commands, which are effectively shell commands, to actually do the generation of that code. This sort of makes sense? So instead of by hand having to every time to remember, all right, I got to run GCC with these flags and I get main.o, we can define a rule that tells make how you generate each file. So this is just classic programming, right? Instead of remembering in your head the algorithm for, say, doing like Newton's method or some complex calculation, you write a program to do it, and then the machine will do it for you. So same thing here. We have mechanization or automation of the build process. All right, so this is what a really basic makefile could look like. Main is the program we're generating, and I didn't even put any prerequisites here. They're not mandatory. And this is the rule we need in order to, this is the command we need to run in order to build it. But this is not okay, so that's an illustration of what a makefile looks like. We have here the target, the thing you're generating, and the command to run in order to build that thing you want to generate. Questions so far? I mean, pretty simple, right? You just literally put the command that we ran here, and then name the thing we're generating, main, here. So it's really common to have a clean target. So there are targets that don't actually build anything. They're just instructions to run. So clean is used to automatically remove generated files. So this is like standard. This is standard practice in build systems. Anything. It's just like doing memory management. If you use any resources, you want to kind of automatically clean them up as well. So clean is just a common target in makefiles. We're only generating the main binary, so clean just removes that binary. All right, so let's see what the prerequisites look like. Prerequisites, here the prerequisites are all of the C files. And so what make does with this, when you specify, actually, I can actually start just writing this. So here's my specification of the makefile. What make does for you is it looks at these prerequisites and it figures out whether you need to regenerate the target. So it just looks at the timestamps and says, okay, if any of these prerequisites have changed, I need to rerun this program in order to rebuild main. So let me show you what that looks like. Okay, so if I run make, oops. So let me remove main. All right, so if I run make, what make is going to do is it's going to say, all right, you want to build main, right? It just looks at the first thing to build in the file, and it looks at these C files and says, all right, if main doesn't exist, I need to run this program in order to build it. So you can see it just actually runs that command for me. And now I've got the main program. Now if I run make again, what do you think might happen? Is it going to build it again? Well, it says it's up to date. How does it know that? So if I take out these prerequisites and I run make, it's still not going to build it because main has been created already. So what make does is it looks at these prerequisite files and sees if any have changed. So if I go in and I edit this main program to take the square of 5 instead, now what's make going to do? It's going to look at these prerequisites and say, all right, one of these has changed, so in order to keep main up to date, I need to rerun this command to build it again. Make sense so far? Now the problem is, it ran this kind of slow command. It rebuilt all of the files. It recompiled everything. So we don't have separate compilation here. We have now some kind of automation to automatically rebuild when any files have changed. We get that kind of for free from make by specifying prerequisites. But we don't have separate compilation. So let's see how we can define that in make. So we can make as many targets as we want, as many rules as we want. So here what we're going to do is instead of having main depend on the source files, we're going to have main depend on the .o files. So it's only going to rebuild if any of these .o files get changed. And then we'll make separate rules for each of the C files. So main.o depends on main.c, and this is how we build main.o for all the .c files. Make sense so far? So what make is going to do is it's going to look at, it's going to try to build main. It's going to look for these .o files. If they're not there, it's going to look for the rules to build them. And if any of these things have changed, it's going to rebuild. Okay, let me show you what this looks like so we can actually see the separate compilation in action. Yeah.
The first command doesn't run still?
This one?
Sorry, the first automation. Yeah, that one will still run if we change we recompile, right?
No, well, if none of the .o file. Well, yeah, if you recompile, it'll still change. Let me show you what this looks like. Okay, so I've run. Actually, So I need a good, clean target here to remove the all the .o files because we can't see it work unless we remove them all. So now we have our C files, our 3 C files, and our make file. I can just remove. Let me just get rid of these other ones, which are superfluous. So we have our 3 C files and our make file. So now we run make. It's going to first try to build the main program, but these prerequisites don't exist. So it's going to look for other rules. It's going to look for these 3 rules to say, how do I make main.o? These don't exist yet, so it's just going to run each of these commands in order to build those .c files. That's what we see here. And then once these are built, make knows that now we have all the dependencies we need in order to build main. So then it finally runs the command to build main. Questions on this? Yeah.
And so it's also keeping aware of the last time it was run and checking that against.
Yes, exactly. Yeah, it's also keeping aware. So yeah, let me show that since you asked about it right now. So if I run make again, nothing's going to change here. Nothing's going to be rebuilt. But if I go in and I say I change exponent to, well, this is just a comment, but so I've changed the exponent.c file. And if you look at the timestamps, you can see exponent has now been modified later than exponent.o, right? So exponent.o is now out of date. So if I run make again, make will say, all right, you're trying to build main. I need these 3.o files. So let me look at the rules to build them. So main.o depends on main.c, but I've already built main.o. So its timestamp is after main.c. So I don't need to rebuild it. Main.c hasn't changed. Same for square.o. But when it gets to exponent, it says, oh, exponent.c has a newer timestamp than exponent.o. That is, it's been changed since I last built exponent.o. So it reruns this rule, and only that rule, not the other .c files, to rebuild that. And then, whoops. And then finally, once it's satisfied all of the prerequisites, the .o files, it will then run the command to build. It'll run the command to build main. Yeah.
So how does the reading of the main file actually work? Like, does it loop back up to the main one, or does it check each one as it's going through that first one?
So what it does, and I wanted to show this in a diagram anyway. So what it does is it says, all right, main depends on main.o. What it does is it builds a tree. It just builds a tree. It builds a dependency tree. And it says, all right, I need square.o, main.o, and exponent.o. And so it builds a tree of these rules. And then main.o says, all right, I need main.c, I need square.c, and I need exponent.c. And each one of these commands, or each one of these files that's generated has a rule associated with it. So it constructs this dependency tree and then finds the timestamps of everything, and it says, all right, if the timestamp below the tree is newer than the root, then run the rule. Otherwise, don't run the rule. So it actually has this like kind of algorithm behind the scenes. It's building this tree of targets that needs to be built, looks at the timestamps to figure out which parts of the tree need to be rebuilt, and then looks to these rules that the developer defined, looks at these rules in order to figure out how to actually generate this file. So yeah, don't worry too much about the internals of Make, but you can look at the manual page as well. It'll like talk about this a little bit. But yeah, it's just basically building a tree of dependencies and then using timestamps to see whether it's sort of like tree walking where you have caching, like this has already been cached, so you don't need to look at the rest of the tree. And yeah, this is how it works under the hood. It builds a tree of dependencies. All right, questions on... Questions on Make so far? I mean, I'm not expecting you to be like an expert on it, but if you just get the idea that you say what you want to generate here, you say how to generate here, and you use this dependency technique to say what depends on it, we can now build these more sophisticated automated builds that we don't have to do by hand anymore. Yeah?
Can we have two make files in the same directory?
You can, but it looks for a default name. And you can specify different files for Make, which like -f. But yeah, there's meant to be only one. That's like the beginning of it. But you can, so one common structure is to have a tree of source files. So you might have like, you know, your drivers directory, your plugins directory, et cetera. And each one of those may have a make file that's called by the top level make file. These build systems can get like pretty complicated. But yes, there are build systems constructed of many make files. They have importing, just like in other languages. You can import other make files. I don't know if that's what you're talking about, but that's a use case where you have multiple source files. But yes, you can have multiple make files. You just have to tell the make tool which one you want to run. Okay, so that's incremental build. There's also some useful linguistic techniques in make files that make it a little easier to write programs. I'm not expecting you to like memorize this or write this yourself. I'll give you examples. But we could have replaced this very repetitive pattern of how to build each C file. We can use these wildcard patterns to instead say, here's how you build any.c file. And don't worry too much about the syntax. It's a little archaic. It's just basically saying any.o depends on that same file stem.o. And the rule is build with GCC-C, and this refers to the prerequisite. But don't worry too much about that. It's just a way to specify patterns of rules. So it's like a meta rule for generating lots of rules. And you also have variables. You'll see this commonly, just like in any programming language, variables, so we can actually automatically collect all the .c file, or we can automatically name all the C files and then automatically get their .o files and generate a rule pattern here. So again, don't worry too much about this. I give you an example make file for the Hello project. And yeah, I'm not going to like quiz you on writing make files. They're pretty esoteric. I usually start from an example rather than actually writing from scratch. And then this is like a kind of a standard template. So if you ever do any larger C projects, this is a pretty standard template for defining a C file project. I know it gets like esoteric as you go up, but don't worry too much about the details. I just want to kind of expose you to it a little bit. If you ever use code from the internet or ever do any systems programming, you'll encounter make files, you'll encounter this kind of esoteric syntax, and just want you to get you a little comfortable with it. But so this is just saying, here's the name of the program as a variable, here's the source files defined, These are all the list of the object files. This just says all and clean are not files that are going to be generated. All is like the de facto standard name of the main target. This is that. This is just this rule encoded with variables, and this is a wildcard rule that is equivalent to these three rules. And then we have a clean rule that just uses variables to say what was generated. But anyway, don't worry about that too much. I'm not expecting you to actually write this code. All right, so any questions so far? So what I really want to instill in you is that there is automation for doing more than just, like when you in your class you're going to be writing single file 100-line C programs. When you get into the professional world, you're going to be dealing with many thousands or millions of lines of code. And this is kind of like the fruit fly of build automation. It's kind of where a lot of this started, this build automation. Now today, you'll hear the term DevOps a lot. You'll hear build automation. You'll hear continuous integration, agile development. All of these software methods, they all kind of can trace a little bit of their history back to the concept of automating build and software operations. And I just want to kind of show you the classic systems tools used for build automation. But any questions on make, build automation, incremental compilation? All right. So I just want to point out that make is a general tool. It's like a programming language. It's sort of accidentally a general purpose language. But it's also used for running tests. You should always be testing your software. People use it for generating documentation, and anything you can run with like bash commands, you can automate with make. Okay, so let me go over the Hello project because this is going to be your first actual project. And in it, you'll have to write code in the command line and actually write a make file in the command line, and then submit it using Git. So it's going to bring together all these three courses to get you like building your first kind of complete C program on the command line, solely on the command line. But to reduce the C programming burden, you're really just going to do Hello World. It's just a Hello World program. So don't worry about the C coding part. Just make sure you get the string right. I've given you the string here. So it sounds easy, right? You're just going to write a Hello World program. Do you ever think you'd have to write a Hello World program for like a sophomore, junior level class? But the hard part is you're going to have to use Emacs or Vim. If you're comfortable with Vim, use Emacs. Use make files to build it. Use a make file to build it, and then use Git to actually submit your project. And so this will add a lot more steps than just running Hello World. So okay, so let me. I'm going to actually walk through. I'm just going to do the exercise in front of you so you can see what it looks like. And then I think I have automated grading working, so I'll also show you what the feedback will look like. All right, let me see if I think I have an old one in here. Let me move this one. Wow, okay, lots of backup files. Okay. So this assumes that you've done the VC exercise, and so that you can set up the repo already. You're already able to set up a repository. But just in case, I've given you the individual commands here. I mean, you could cut and paste these, but if something goes wrong, then consult the VC documentation for how you actually set this up. So I'm going to walk through all the Git setup steps, which are outlined in great detail in the VC project. So I'm just creating a new folder called Hello, and I'm entering that folder. So I've created the Hello folder under my COP-3402 Fault 25 directory in Eustace. I'm in Eustace. And now I'm in my Hello folder. It's empty. There's nothing here. Git init will create the repository. I always have you start with a README, which is kind of like good practice and also gives you a way to actually create and push the repo. And then this one is a lot easier to just copy. This is the remote grading repo, and check the check the project for how you can verify this stuff, check the VC project. And then we're going to push this. Oh, and this is probably from last semester. So I have to, so I already have a hello project. So let me just I'm going to give it a different name, but. Okay, so now this is the VC project. This is the same thing as the VC project. This is what our repo looks like. All right, so here's what it's going to look like to actually do the homework. So we're going to, so one little wrinkle here is to actually prove that you're using the command line. I'm going to record you on the command line doing it. So you're actually going to record yourself. So there is this, to sort of avoid using VS Code or anything else, there's this tool called Script, which will actually record everything you write on the terminal. These are actually useful tools for generating tutorials and stuff like that. So now I'm recording my terminal session. And so here, I'd like you to write your Hello World program. Don't worry if it takes you a long time, or don't worry if you make mistakes. That's okay. So it's going to record me doing this. Don't forget the new line character. All right, and let's make sure it actually builds. And voila, it works. So exit will stop recording. And now I've created this script file. And the script replay tool will actually run it for me. So look, no hands. It's happening by itself. And it's not actually editing anything. It's just showing you what was on the terminal. So just prove it, look, no hands, yeah.
Obviously, it's not a big issue for this project, but does this mean you have to do it all in one go, essentially? Write the program all at once?
Yeah, basically. But it's a Hello World program. So I hope you can do that in one go. If it takes you a little longer, that's okay. But I was sort of hoping everyone could do Hello World, in a couple minutes.
What about future projects?
No, you don't have, no, not at all. Not at all. And you can use other editors too. You don't have to use Emacs. All right, so that's creating the Hello World program and creating the recording of you actually using Emacs. Let's actually use it once. Don't use Nano. Use Emacs or Vim, or just use your own editor on your local machine if you want. All right, and then the next tricky wrinkle here is using the makefile. So I don't have you record this because this will take a little bit more trial and error. So just write out this main make program because we're going to use this for all of our projects. So in order for our automated grading to work, I don't want to have our TAs sit and figure out how to build each of your projects. So instead, you give us a make file. And this is the beauty of build automation, is that you can give somebody else your code and they don't have to know how to build it. You just say run make, and voila, your make file should do all the building for you. If you've ever downloaded other people's code or had to build other people's code, this is preferable than having to read through documentation and build stuff. So the requirement for all the projects is that we clone your project, we run make, and we run the program. And that's it. That's all we're going to do. So if that doesn't work, then the grading's not going to work. We're not going to be able to run your program. So that's what also build automation does. It's kind of like mechanized documentation. All right, so let me quickly write out this. And one wrinkle here is that these look like spaces for indents, but they have to be tab. This is a very kind of archaic thing, but they have to be a tab character. So if you encounter an error, so let me run this make file. So this is what it should look like. It should just run GCC. But if you accidentally use tabs, this is what it's going to look like. It's got to say missing separator. Did you mean tab instead of 8 spaces? Why, yes, I did. I did mean that. So just make sure these are the literal tab character. It's actually a different character in ASCII code. All right. What's that? I didn't, but that's okay. Actually, yeah, I probably should put it because there's a. Okay. So one little note here: some people, for some reason, run their program with make, like after it builds. This is very annoying for automated scripts, so don't do that. Just run the program. You can make another target if you wanted, but it shouldn't be hard to just run the program. You don't have to run it in make, and that's kind of atypical for the build step anyway. Okay, so to test to make sure this is working, make sure clean works, So make sure it actually removes the main program. When you run make, you should see the build step. And if we run make again, nothing should happen. So you shouldn't be surprised if you see nothing to be done. It means that your program's already built if your make files run correctly. And then I have some other steps in here. You can follow, well, let me see. I have a few minutes. All right, let me follow along with these. So another useful tool in Git, if we run git status right now, there's a lot of files. There are some files that we don't need to submit, like binaries. So source version control is called source version control for a reason. It's not meant to hold the binary programs. It's meant to hold the source code and build automation so that someone else can rebuild your code. Much less space, usually. And also means that you can rebuild it for somebody else's platform. You don't have to get their binary. It also means you can review their code and not trust their binary. Okay, so let me, where do I have this? All right, let me, I'll submit this so we can see what this looks like, and then I'll show the git ignore stuff. So I'm just gonna commit all these individual files. I'm going to add the timing files and script files. And add the make file. Okay, so you can see that now I've committed them all, and so it just says, well, there are these like 2 extra files. I don't need to commit the hello file or the make file. But it's kind of annoying to have these being, Git telling us that these are untracked all the time. So there's a special file called .gitignore where you can put these files, put the names of these files, and Git will look at the gitignore file and say, oh, okay, if they're in the gitignore file, they should never be tracked. They should never be part of the repo. And notice that now gitignore itself is also now a file. But we don't want to ignore that. We actually want to add that to our repo. And now we have a clean working tree. So those extra files, even though they're not part of the repo, they're not meant to be part of the repo, they're going to be there when you build your program. It's going to be there. But gitignore will hide them from your view, so you don't, so it's easier to see if you have any changes that haven't been pushed yet. All right, let me push these changes, and then let's see if I can actually, and then I have some illustration of how to do a self-check to make sure you have everything right, and let me see if I can actually get grading done. So it's the hello grader, but I need to, what repo did I use? Hello fall class. Hello fall class. Let's see if I can do this without breaking this time. Okay, I think it actually went there. Let me show you the feedback. So here's my feedback folder. I now have this hello fall class folder. It's just going to be called hello for you. You can see we have a file time-stamped to the time that it was graded. And inside, it'll be the report, your grading report. So it'll show you whether we saw that it actually existed. If it didn't exist, your feedback may not exist either, so you might not even see that. Whether you have the required files, make sure you didn't submit the binary, make sure you actually use Emacs or Vim, and then check whether make worked and the program worked. Okay, so that's what you see in the report. Good luck on the Hello project. Have a good weekend, everyone. And yeah, thanks for the extra minute. Take care, everyone.